Alrighty, here we have this integral that we're given, 1 over 4 plus x squared dx, and you need to integrate this. The trick here is recognizing that regular substitution is not going to be very useful. There's nothing that one would obviously choose as a substitute to replace. So, that leads you to think about perhaps integration by parts, but again, there's nothing that you can do there that's going to make this any less hard to deal with. So that's going to bring us up next with trig substitution. And the idea here is to pick some trigonometric identity that's going to resolve this whole nasty 4 plus x squared mess. And tangent will do the job nicely, I think. So we're going to say let x equal tangent. So x equals the tangent of theta. Note that's a different variable. We are doing substitution, so we have that going for us. Now the reason that you would want to use trig substitution is to get this x term in a form that in some way or another will leave us with a trig identity that we can simplify, particularly one in advance that's going to be useful with the derivative of x once we've done our substitution. And tangent all by itself isn't quite there. It's going to be off by a factor. So if we think of 4 as 2 squared, then we have 2 squared plus x squared. So we have something squared plus something else squared. And we want to be able to factor at some point, so we need to put a coefficient on our tangent there that's going to make it factorable with this 2 squared, this 4. And since x is going to be that whole thing under the square, 2 will do the job nicely. And that is going to leave us with one over 4 plus 4 tangent squared theta dx. I haven't done the part with dx yet, so I'm still keeping this dx. I'm going to factor this. 4 is common to both, so I can pull that 4 out. And have it in this form, 4 times the quantity, 1 plus tangent squared, theta, and then my dx here. Well, I have x, and I've got a theta, so now I've got to figure out what dx is. It'll be the derivative of x with respect to the new variable we're working with, theta. So we'll differentiate both sides. I have, serendipitously so, an earlier video that deals with demonstrating the derivative of tangent. It's something that you should probably just memorize. It's secant squared. The coefficient 2 doesn't have a theta or an x term, so it just comes along. It's unaffected by the derivative. And as I already said, the derivative of tangent is secant squared. Remember, we're now dealing with theta, so that's going to be 2 secant squared theta. I need to find dx, but what I have here is not dx. I have dx over d theta, so I need to find out what exactly dx is. If I separate this and move the d theta to the other side, I will find out precisely what dx is equal to. Dx is exactly equal to 2 secant squared theta d theta, which means I can now replace that here by substitution. And if you're not that savvy with your trig identities, this is not going to appear to be terribly fruitful. But 1 plus tangent squared is secant squared. So I can replace that with the denominator here being 4 secant squared theta. secant squared cancels with secant squared. 2/4 will reduce to 1/2. That's going to leave me with integral 1/2 d theta. Fairly direct integration here to do. The integration of a constant with respect to a variable. So that's going to be 1/2 theta plus c, or theta over 2 plus c. But we're not quite done yet, because we started off with something with respect to x, and we've ended up with something in terms of theta. So what we'll need to take into account here is that we had that relationship between x and theta. So if, I'll just rewrite it over here. If x equals 2 tangent theta, and we're trying to find it in terms of x, when we know something about theta, then we're going to have to use our inverse trigonometric functions and solve for theta. And that'll get us back to having this in terms of x, the inverse tangent, take the inverse tangent of both sides. So theta is going to be exactly the inverse tangent of x over 2. This is no longer true because this is in terms of theta. So I would restate my original problem. And that is your answer. X, X, and X. So I don't have anything left in terms of theta. And I've got the complete solution here for that indefinite integral.